How's it going? And in this video, we're going to be looking at multiple logistic regression from scratch. We'll look over the math, intuition, and implementation of it in Python. And to start, we're going to look at just basic logistic regression, which takes in a single X feature input. And we're going to create some example data and see what it's like to make predictions on that data. Then we're going to go over the cost function and the gradient descent algorithm for logistic regression. And once we have a good foundation on that, we'll move into multiple logistic regression, which will have multiple X features and an updated cost function and gradient descent algorithm. And just as a quick note, for the implementation in Python, I'll be using Jupyter notebooks with the NumPy, Matplotlib, and scikit-learn libraries installed. Alright, and to start logistic regression, let's come up with some example data. So for this data, we're going to use whether a student passed or failed their exam depending on how many hours they studied. Alright, so here we're looking at 5 different students. On the left we have the amount of hours they studied for the exam, and on the right we have whether they passed or they failed the exam. A pass is marked as a 1 and a fail is marked as a 0. So we have the first student studied 6 hours and they passed. The second student studied 1 hour and they failed. And let's also say that the first student can be marked with index 0. The second student is index 1, going all the way down for all m students. And then we'll also say x at I is going to be equal to the number of hours the ith student studied. So if we have x at 0, we're looking at 6, and x at 1 is looking at 1. And the same thing can be said for y, where y at I is whether the ith student either passed or failed the exam. So y at 0 is 1, and y at 1 is 0. And with that notation out of the way, let's get into plotting these points on a graph. Alright, so in this graph we'll have the x-axis be the number of hours the student studied, and the y-axis be whether that student passed or failed the exam. Alright, so the objective of logistic regression is to find some decision boundary where everything on one side of the boundary is of one class and everything on the other side of the boundary is of another class. So if we had a decision boundary here at around x equals 2.5, then we might want to say that everything to the right is a pass and everything to the left is a fail. And that just means if a student studied 2.5 or more hours, then they likely passed. So everything in this region of the x-axis. And if they studied less than that, then they probably failed, and that would be in this region. And one way that seems intuitive to find this decision boundary might be to create a line of best fit on our data, where in this line of best fit, say this is where y is equal to 0.5. Any x value that yields a y greater than 0.5 would be a passing grade, so anything up here. And any x that yields a y of a value less than 0.5 would lay somewhere down here. So if this was y equals 0.5, then anything above it would pass and anything below it would fail. And in something like linear regression, this line might be represented by something like y hat equals wx plus b, where y is the resulting value, w is the slope, and b is the y-intercept, where w is also called weight and b is also called bias. And before we move forward, let's actually erase this y hat, because we'll be using a different y hat variable for something else later, and we'll just use wx plus b to represent this line for now. Now we could go through linear regression and figure out how to best fit a line to the data, and then just take y equals 0.5 as the boundary, where anything above it is a pass and anything below it is a fail. But it turns out with logistic regression, there's another equation that we can use to increase accuracy even more. And that's known as the sigmoid function, which looks something like this. And just to see what this function looks like, let's graph it. So if we had z on the x-axis and g of z on the y-axis, and we have some x and y ticks on this graph now, then let's look at what g of 0 might look like. So g of 0 is equal to 0.5, which is right in the center. G of 1 is about 0.73, which is around there. And g of negative 1 is about 0.27, which is around right there. And if you continue to plot points, you would get a line something like this. And as z approaches infinity, g of z would approach 1. And as z approaches negative infinity, g of z would approach 0. And now let's use this g of z, or sigmoid function, back in the context of logistic regression. So instead of just using this wx plus b to find the decision boundary where y is equal to 0.5, let's actually plug wx plus b into this z variable in the sigmoid function. And that way we'll get a very stable result in predicting where y is equal to 0.5. And so the result of this might look something like g of wx plus b. And we'll call this function f of x with subscript w and b. And to gain some intuition on this new f of x function, let's actually plug in some values for w, x, and b, and then apply those through the sigmoid function, which first we'll need to know what our w and b are, so let's kind of eyeball that. And for our w, or our slope, it looks like we have a run of 6 and a rise of 1. And our bias is right at 0. Now let's plug in some example points to wx plus b. First we'll look at this point right here at x equals 1. Alright, so at an x input of 1, wx plus b results in a y value of 0.16 repeating, which is right around here on our line. And let's plug in one more point. Let's do when x is equal to 4, so looking at this point right here. Alright, and when we're looking at an x equal to 4, we get this point right here, and that's where y is equal to 0.6 repeating. Now let's apply these values that we just got into our sigmoid function up here. So we'll have f subscript wb of 1, and that's equal to g of this 0.16 repeating that we just calculated. And now g of 0.16 repeating is equal to 1 over 1 plus e to the negative 0.16 repeating. And finally, that gives us about 0.54. And let's do the same thing for this 4 down here. So we have f subscript wb of 4, and that gives us g of 0.6 repeating. And then plug that into the sigmoid function. And from that, we'll get about 0.66. So now let's plot these points on our plot up here. So we had an x value of 1 and a y value of 0.54, somewhere around here. And then when we had x equal to 4, our y value was 0.66. That'll be somewhere right here. And if we continued plotting these points, we might get a line something like this, which, as you can see, our y equals 0.5 is a little further to the left than we would like it, but that's okay. We're going to be training a model using logistic regression. And for argument's sake, let's say we actually did complete training a model and we got our sigmoid function to create a line for us right at that decision boundary line, right through the middle right here. Then at this point, anything that's above 0.5, again, is going to be the passing, and anything below 0.5 on the y is going to be a failing grade. Then what we can say is y hat at I is going to be equal to when f of wb at x of I yields a value greater than or equal to 0.5, then y hat at I should be 1. And if x subscript wb of x of I is less than 0.5, then y should return 0. And these are our predictions whether the student either passed or failed. And so it's common to write this probability function, p, that y is equal to 1 given x, is equal to f of x. And so all this is saying is the output of f of x is going to return the probability that y should be equal to 1. So if we plug in a 1 for x, then we would get a 54% probability that y is equal to 1. And in another example, if we plugged in 4 for x, we would get a 66% probability that y is equal to 1 given that value of x, which was 4. All right, and now that we have our example data and a y prediction function, we're ready to jump into Jupyter Notebook and start coding. All right, now let's start coding out the section for logistic regression. And we're first going to start with initializing the x, y, weight, and bias values. And we're going to use these same values for x and y, but let's format them a little bit differently by putting x in order just so that some plots later on look clean. Alright, so we still have when x is 1, y is 0, when x is 2, y is 1, and so on. So let's initialize our weight and bias now. And now we can write out the functions for the sigmoid and predict y. Alright, so our sigmoid function is just like we wrote on the whiteboard, where we have 1 divided by 1 plus e to the negative z. So sigmoid is 1 divided by 1 plus e to the negative z. And now we can write the predict y function. Alright, so for predict y, we're passing in x, w, and b, and then initializing an array with the size of the training data. And then in each of those elements in yprobs, we're calculating the probability using these functions right here. So we're calculating the sigmoid of wx plus b, sigmoid of wx plus b, and then it's actually the probability that's being calculated from f of x. So we're storing that probability into yprobs at I. And then in ypreds, we're using the np.where method, which looks at each element in yprobs, checks to see if it's greater than or equal to 0.5. If it is, store 1 in ypreds at I, otherwise store 0. And this is essentially doing that piecewise function that we looked at earlier. And so let's test these out. Oh, and I just noticed I accidentally did a 1.66 instead of 0.166. So I'll change that really quick. Alright, and here are the outputs. As you can see, they all got predicted as a passing grade on the exam. And that's because we looked at earlier, this sigmoid function ended up being way over to the side, so everything was predicting a 1. And we can play around with the weight and bias a little bit in a second and see if it gets different results. But first, let's try to plot what x looks like against y, yprobs, and ypreds. Alright, so in this plot we have y true on the bottom and on the top, showing the true y values for x. And then yprob is the result of our sigmoid function. And then ypreds is what we actually calculate in the np.where, where we collapse it to either 0 or 1. And this graph might be a little bit difficult to see, so let's actually update these values so that we can have some better visualizations. So first, I'm going to add a 0 to the x and the y, saying someone studied 0 hours and then they failed. Let's use a different weight and bias. We'll use 2 and -3. And if we run through this code again, alright, so maybe this plot's a little easier to visualize what's happening. So this is a better fit line if we have y true as the blue dot still, and yprob as the output of our sigmoid function, then the probability looks more like a sigmoid curve like we were looking at in this whiteboard example up here. And ypred is collapsing to either 0 or 1 when it's either above or below this boundary line of 0.5, which that was our threshold that we used. Alright, so at this point we've set up a prediction function that takes in x, w, and b and predicts y and compares it to the true values. Let's go ahead and check out the cost function to see how well or how poorly our model's doing. All right, now that we're back to the whiteboard, we'll want to isolate this graph right here before going into the cost function. Now, one common cost function is the mean squared error function, which looks something like this. And this is the cost function that's used in places like linear regression, where we're basically just taking the error of the true values with their predicted values, summing all those up and squaring them, and then dividing them by m to get the mean. But for logistic regression, this will give us some issues later on when we go to gradient descent. So let's look at a different function called the log loss function, which looks something like this. All right, now notice how this loss function is a piecewise function, where if y of I is equal to 1, or a passing grade, then we're looking at the top. And if y of I is equal to 0, or a failing grade, then we're looking at the bottom. Or in other words, if we're looking at the loss of the predicted value when x is equal to 4, so if we predicted this value at around 0.75, and the true value was 1, then we would look at this function because our true value is 1. And on the other hand, if we're trying to predict whether the student passed at 3 hours, we would be looking at this point right here, which is about 0.6. But it turns out that student failed, giving us a y of 0. Then that y of 0 would correspond to this function right here to calculate the loss. And to gain some extra intuition to what these two functions are doing, let's actually plot them. All right, so in these graphs, I'm substituting p for this prediction function right here. If you plug p into both of these functions, they'll end up looking something like this. All right, so a few things to notice in these plots. P is going to represent our predicted probability that the student passed the exam. And the left plot is when y is equal to 1, or when the student did pass the exam. And the right plot is when y is equal to 0, or when the student actually failed the exam. So let's pull some numbers over from our graph so that we can get a better understanding of what these loss functions are doing. So let's first look at the student who studied for 4 hours. They passed the exam, and we said there's a 75% probability that they passed the exam. And let's also look at the student who studied 3 hours, failed the exam, and we came up with a probability of 60% that they passed. Now, given these two students, notice how the first student had a true value of y equals 1, so their loss is going to be determined by this graph to the left. And the student who studied 3 hours failed the exam with a y equals 0, so their loss is going to be determined by this graph to the right. All right, so if we plug in the probabilities to this function up here, we would say p is equal to 0.75, which is around right here, and that would give us this value on the y-axis, which turns out to be around 0.12. And if the student actually had a probability much lower, something like 10%, then that would mean the true value was that the student passed, but we guessed that they probably failed the exam. So that should result in a higher loss. That would give us a much higher value on our negative log of p. That would actually result in a value of 1. And this is actually what we would want. So if our prediction was very close to the true value, we would want a low loss. But if our y was still equal to 1, but our prediction was much closer to 0, then we would want a much higher loss. And now let's look at the example where the student's hours were 3 and they failed the exam. So again, that would be pointing to this plot right here. So if we plugged in 0.6 as the probability, which is around right here, we would get a point on the y-axis around right here. And this point is actually around 0.6 as well. And to give another example for this plot, let's use that 10% prediction again. So if we said there was a 10% chance the student passed the exam, that would give us a point right here, and that would result in a loss right around here. And this point is about 0.05. So again, if the student failed the exam, and we said that there was a 10% chance that they passed, or 90% chance they failed, then there should be a very low loss. Whereas if we said there was a higher chance that they passed the exam, say over 50 or 60% chance in this case, then we would have a much higher loss. There's actually a little bit cleaner of a way to write this function right here so that it's not a piecewise. So let's go ahead and write that out next. Alright, so in this function, there's a few different parts to it. So notice how the loss represented when y is equal to 1 is in green, and the loss when y is equal to 0 is represented in red. If you plug in either a 1 or a 0 for y, you'll end up getting the same results as this piecewise. So for example, if y of I was equal to 0, you would have 0 multiplying against this green part, so this all would cancel out and turn to 0. And then you would have 1 minus 0, or just 1, times this red part of the function. So in the end, all you would get was this side of the function. And on the other hand, if y ended up being 1, so the student actually passed the exam, then on the right side, you would have a 1 minus 1 equals 0, and that would multiply against this red portion, canceling it out. And then you would have a 1 times this green portion, and so you would only result to using this green half of the equation. Alright, so at this point we have the finished loss function, but this is only going to be looking at a single true value with its predicted probability. And what we want is a cost function that does this for all of the points in the graph and gets the mean of this loss, similar to how the mean squared error function operates. So now we're ready to apply this loss function into a cost function. And for this cost function, let's use this idea of taking the mean of the losses like we do in mean squared error. So we'll have a cost function that looks something like this. And then if we wanted to expand it out further, and here we have our finished cost function. So let's go ahead and code that up in Python. All right, so in this section, we're calculating the cost. And let's go ahead and write out that function right now. All right, so here's our cost function. We want to iterate over all m training examples and then initialize cost with 0. And then in the for loop, we're going to calculate the y prediction for each of our training examples and then plug that into our loss function and then add that to our cost for each training example. And then finally take the average of those losses and that will be our cost. And one other critical point to mention is that log of 0 is actually undefined. So it might be nice to add some small value inside of these log functions so that we don't get an undefined error. Alright, so here we're going to initialize this ellipsin at 10 to the negative 5. And if we apply that ellipsin into our log functions, we should never get an undefined error because FWB has to be in the range of 0 and 1. Alright, so now let's test out our cost function. Alright, so it looks like the cost function gave us a value of 0.62, but it looks like on our plot above we got some pretty good predictions. So if we used a value of W plus 5, we would probably get a worse cost because we likely wouldn't get as good of predictions as we had right here. So let's test that cost function again, but with W plus 5. Alright, and just like we predicted, a much higher weight value gave us a much higher cost. So it looks like our cost function is working, and now we're ready to move on to gradient descent. Alright, and to help us gain some intuition as to what we're doing with gradient descent, let's first plot out the cost function. And in this case, let's just assume the bias is some constant value, and we'll see how the cost is affected by changes in W. So as we saw a second ago, when W was equal to 2, we had a cost of 0.62. And when we added 5 to that weight, the cost went up to 2.59. So if we plotted the weight values with their corresponding costs, it would look something like this. And if we kept testing different values of W and plugging them into our cost function, we would end up getting a graph that maybe looks something like this. So notice that when our weight is just right, here at this global minimum, we're probably making really good predictions as to if students passed or failed their exam. Whereas if our weight was way off, like at 7, then we're probably making much worse predictions whether students passed or failed. So that would result in a higher cost. And similarly, if our weight was way too low, we would probably also be making bad predictions, and that would also result in a high cost. And in logistic regression, we can initialize W to either 0 or some random value. So if we initialized it to say 7, and then looked at the slope of the line at this point, and then if we picked a different W, say 1, then the cost function at that point would have some decreasing slope. And if the objective was to change W in some way to minimize cost, then we can see that with a w that's too high, and if we have an increasing slope, we want to decrease w to result in a lower cost. And similarly, if our w is small and the cost function had a decreasing slope, we would want to increase w to lower our cost. So let's write out that observation to the right. So with a positive slope, we want to decrease w, and with a negative slope, we want to increase w. So at this point, it looks like if we can figure out what the slope of our cost function is at some given w, then we can figure out if we need to decrease w or increase w. We can find the slope of j of w given any w input by taking the derivative of j. Or in other words, we can say the slope is equal to the partial derivative of j with respect to w. And now that we have this partial derivative term, we can actually say we want to decrease w by that term. And so if the slope is positive, we want to decrease w. And if the slope is negative, then we want to increase w. And then one last variable we're going to add in here is alpha. And alpha is equal to the learning rate. And by introducing alpha, we're ensuring that by changing w, we're not changing it by too much of a value that would end up increasing our cost. Instead, we're just nudging our w in the desired direction. And also notice how once we get closer to the global minimum, the magnitude of our slope decreases, so we're going to end up taking smaller and smaller steps until we hopefully converge at that global minimum. Alright, and let's actually rewrite this step down here, and we'll want to repeat it multiple times, just like how we showed that we want to take multiple steps up here. And we can say we want to set w to itself minus alpha times the partial derivative of j with respect to w. And if we were to exchange w for b in this graph, we would be accomplishing the exact same thing. So we could add to our algorithm b is equal to b minus alpha with the partial derivative of j with respect to b. And again, these two derivatives are looking at the slope of the cost function with w as an input and then with b as an input. So now all we need to do is derive these two terms from this cost function up here. So let's go ahead and write the solutions to those two partial derivatives. Alright, so it turns out when we take the partial derivative of j with respect to w and with respect to b, we get this equation on the top for w and this equation on the bottom for b. And at this point, we can plug these equations into our algorithm. So let's go code that out in Python now. Alright, back in the notebook, let's first calculate the gradient and then we'll apply it repetitively in the gradient descent algorithm. Alright, so here we have the function that calculates the gradient given x, y, w, and b. First, we're going to initialize m to iterate over all training examples. And then here's our gradient initialized, which is essentially just the partial derivative of both w and b. And then when we iterate over all the training examples, we're first going to want to calculate that f of wb, which is our predicted probability. And then we want to calculate the error between that probability and the true value, which if we look back at the algorithm, we're finding the predicted probability, subtracting it from the true value, and then adding the error times x at I to dj dw. So we're multiplying that term by x of I for dj dw, and then dj db just takes in the error, like so. And then finally, we want to divide both dj dw and dj db by m. So we're doing that here. And then we can return both of those terms. So let's go ahead and run this function and see if we can use it to improve our cost. Alright, so looking at this code block, we printed out the initial w and b with its corresponding cost, which that's shown in this first line here. And then we calculated the gradient and printed out the gradient values, which are shown in this line, and then initialized some small alpha of 0.01, performed a single step of our gradient descent algorithm, which is again this algorithm right here, and then printed out the final weight, bias, and cost, which that corresponds to this line right here. So it looks like our weight and bias dropped by a small amount, and that also lowered our cost. So it looks like our calculate gradient function worked, and we're ready to move on to gradient descent. Alright, so here's our gradient descent algorithm all written out. We're going to pass in x, y, w, and b, initialize alpha, or our learning rate, to 0.01. We're going to go through 1,000 gradient descent steps, and every 100 steps we're going to record the current cost. So looking into the function, we're going to initialize this empty history dictionary to store the costs, and then in each iteration, we're going to perform a single gradient descent step. And then this if statement is going to be called every 100 iterations, and it's going to store the current cost to history and print it out. And then we'll return the history, the weight, and the bias. So let's run this function to see how well it works. Alright, so after running that function, it looks like our cost started up around 0.62, and then over time it went down to about 0.4 and then flatlined. So let's go ahead and plot this history so we can visualize it. Alright, so here we have a visualization of the cost over all the iterations. And with that, let's plot some predictions again. Alright, so in this graph, the blue dots represent the true y values, and the x's represent the predicted y probabilities, where the red x's are the probabilities before gradient descent, and the green x's are after gradient descent. And notice how in the old probabilities, the red x's were tending to be a little too high, and after gradient descent, they kind of leveled off to have a clean break in between all of our data. Alright, so it looks like our gradient descent algorithm worked pretty well with one x feature, but let's now try out multiple x features, and that'll lead us into multiple logistic regression. Alright, and back to the whiteboard, let's take a look at multiple logistic regression, and to do that, let's create some more example data. Alright, so now in this data, we have hours and GPA to help us determine if a student is passing or failing their exam. So notice that we're still predicting a single y value, but we now have two x inputs. And to distinguish these two x inputs, we can use a subscript. So hours can be x of 0 and GPA can be x of 1. So we might also want to denote that subscript value as j. So we could say hours is x of j when j is equal to 0, and GPA has j equal to 1. And then we can also say that n is equal to the number of features. So in this case, n would be equal to 2. And then we'll still use I to denote each student index. Alright, so now let's try to plot these points on a graph, but notice that we have two different x features, so we can't just do an xy plot anymore. Instead, let's do a plot where x0 is on the x-axis and x1 is on the y-axis, and then we'll mark the passing grades in green and the failing grades in red. Alright, now that we have these points visualized, let's reintroduce that decision boundary. So the decision boundary might look something like this. And looking back at our original graph with a single x feature, we can notice that this right side, where our prediction probability is closer to 1, is a passing grade, and the predictions to the left have a higher probability that the student failed. Then also notice more toward that decision boundary, we're approaching that y equals 0.5 region. Now, if we apply that same concept of the height of y to this graph with two features, we would have a highlight that looks something like this. So notice how predictions to the top right would be a higher probability that the student passed, whereas predictions in the bottom left would have a higher probability that they failed. And I hope that builds some intuition to what the sigmoid curve looks like on this 2D plot. Now let's write out the equation to use that will actually give us these sigmoid results. Alright, so this is the equation we were using earlier when we had the sigmoid line on that single x feature plot. But now we have two x features and we want to use both of those in predicting y. But before we only had a single x input, and now we can't fit both of these x's into that single x input. So we'll need a new way of calculating that wx plus b. So let's take a look at what this new wx plus b should look like. So first of all, we're going to be using both of those x values. So we want to get x of 0 at I and x of 1 at I. And now we're going to want a different weight value to apply to each of these x terms. So for that, let's multiply x0 by w0 and x1 by w1. And then after multiplying these two terms, we can add them together. And since b was already on its own and not connected to any x values, we can go ahead and add that to the end again. And it turns out this w0 x0 plus w1 x1 can also be represented as a dot product. And then we'll want to tack on that plus b. And just to clarify, this dot product is the exact same thing as saying w0 x0 plus w1 x1 plus however many wn xn you have. But with this piece calculated, we can go ahead and plug it back into our sigmoid function. So the only change we need to make is take the dot product between the vectors w and x, and then let's go ahead and make the updates everywhere else. And with that done, this graph now represents this equation. And one last thing to mention is the equation of this line turns out to be this. Which this is just saying if you had some weights and bias already initialized and then plugged in some value for x0, x1 on that y-axis would mark a certain point. Alright, and with all that written out, let's go back to our Jupyter notebook and make some predictions. Alright, and for this part, we're going to want to initialize some x, y, weight, and bias again. And let's go ahead and use these values we have here. And then we can initialize some random values for weight and bias. Just know that the length of the weight needs to be equal to the number of features, which is 2 right now. Now let's go ahead and plot these points. Alright, so in this plot, we have these green points marking where y is equal to 1, and these red points marking where y is equal to 0. And again, green is if a student passed the exam, and red is if they failed the exam. Now let's also add our current decision boundary to see what that looks like. And again, here is our function to calculate the decision boundary. Alright, so here we have the decision boundary in our training data, and it looks like the decision boundary is a little too low and it needs to be raised up. But let's actually wait and see if we can achieve that later using gradient descent. And until then, let's go ahead and write out that prediction function. Again, we'll be using this function right here. Alright, so here's our predict y function. It takes in x, the weight, and the bias, and then it creates an empty array for all of the probabilities. And then over each training example, we're calculating the z, inputting that into our sigmoid, calculating the probability, storing that into our probability array. And then finally, we're creating a threshold of 0.5. Anything above 0.5 will be stored as a 1 prediction, and anything under it will be stored as a 0 prediction, and then we're going to return that. And actually, let's also return that probability and test out the function. Alright, so as expected, the probability that each student passed the exam was pretty high, and so we predicted that they all passed. And that would actually make sense because our decision boundary right here would tell us that anyone above the line was predicted as passing, while anyone under the line was predicted as failing. And as we know, some of the students did fail, so they shouldn't have gotten such a high probability that they passed. So let's actually calculate how wrong our model actually is by looking at the cost function. Alright, so we're back to the whiteboard, and to help us figure out the cost function for multiple logistic regression, let's actually refer back to the one we used for logistic regression with a single x feature. Okay, so here's the cost function we used earlier, and it turns out all we really need to do to this is apply those vectors that we determined a minute ago. So those vectors are on x of I and w. So here we're still predicting a single value for the probability of y and plugging that into the log functions. So by applying this vectorized form to the w's and the x's, the math should still check out for the cost. So now let's implement that in Python. Alright, back to the notebook, let's write out our cost function. Alright, so here's our cost function, and as you can see, it looks very similar to the one we looked at earlier. We're starting with the cost of 0, going over each training example, calculating the probability, then inputting that into the loss function, and then adding it to cost. finally dividing by m and returning the cost. So let's run this and see what kind of results we get. Alright, so we got a cost of a little over 2, and that's likely a pretty high cost considering that our boundary was so off from our training examples. So let's move into gradient descent to see if we can improve that cost. Alright, so let's first rewrite out that gradient descent algorithm we used for logistic regression as well as the gradient math. Alright, and so here on the left we have the gradient equations for logistic regression as well as the gradient descent algorithm on the right. And let's see what needs to be changed about the logistic regression gradient descent so that we can fit it to multiple logistic regression. And the first place we'll want to look is at this W term right here. And remember that we're not using a single value for W anymore. We're using an entire vector where we have a weight corresponding to each feature in our training data set. And so what we're going to want to do is take the partial derivative of j with respect to W0 and then with respect to W1 all the way up to this final weight value. Or in other words, we're going to want to take the partial derivative of j with respect to W in this equation up here, looking at the jth W element. And by taking that jth partial derivative along with updating our function to work with multiple logistic regression, we would get a new equation that looks something like this. Alright, so all we did was add the vector notation to the weight and to the x to fit our new probability function, and then we added a j to x of I at the end right here. And that's because in our probability prediction function, if we were taking some partial derivative of a w at some j value, for example, if we set j equal to 1, then we would be looking at the partial derivative of j at 1, which is this term. And here x of 1 is the coefficient, so it would get pulled out. And this process is all just part of the chain rule when finding the derivative. So let's now update this right side in our gradient descent algorithm. We're going to want to update w at j now, setting it to itself minus alpha times the partial derivative with respect to wj. And we'll want to do this for each j. So we'll be doing it for w0, w1, all the way to wn minus 1. Alright, now let's update the partial derivative with respect to b. So as we saw earlier, b was on its own. So if we had some w dot x plus b, then b is not attached to any coefficients, no x's. So no x would need to be pulled out when finding the derivative due to any chain rule. So all we would really need to do is add that vector format to the w and x's, and no further changes need to be made to our gradient descent algorithm. Alright, and with that math and algorithm done, we can go ahead and implement this in Python. Okay, so let's create a new section for gradient descent. Alright, and like we did earlier, let's write a function that just calculates the gradient, and then we'll write a separate function to apply that in the gradient descent. Alright, and here we have our function written out to calculate the gradient, and let's test that out with a single gradient step. Alright, so looking at the output of this code, it looks like our cost went down by a very small amount from one gradient step. So it looks like our calculate gradient function is working, and now we're ready to move on to gradient descent. Alright, so here we have our gradient descent function. We're passing in these x, y, w, and b values. We're starting with a learning rate of 0.01. We're going to go over 1,000 iterations with a history step of 100. Again, history step is to record the cost every 100 iterations. And then in our for loop, we're applying gradient descent steps in each iteration. And at the end of this function, we're going to return history and the updated weight and bias. So let's run this and see what kind of results we get. Alright, so it looks like we started off with a cost of around 2 and then almost immediately dropped down to our minimum cost. So let's visualize this on a history plot. And just like what we saw above, we started off with a high cost, dropped off immediately, and leveled off at a minimum of around 0.2. So now let's plot what these results look like. Alright, so in this plot, we're passing an x, y, w, and b, and creating some y predictions from the training data. And then we're going to start up a new plot and scatter the true values for y, and then scatter the predicted values for y using an x marker. Next, we'll plot the decision boundary with a gray dotted line, and to give some final context, we'll add a legend, a title, and the x and y labels. So let's run this function with our new w and b. Alright, so as we can see in this plot, the y equals 1 values are on the top, and the y equals 0 values are on the bottom, and it looks like our decision boundary is cutting straight through the y equals 1 and y equals 0 values. So because of that, we see y hat equal to 0 is at the bottom with the y true equal to 0, and the predicted values equal to 1 are on the top with the true y equals 1 values. So from this plot, it looks like our gradient descent algorithm is working pretty good. So now let's go ahead and generate some more data to test against. Alright, so to generate our training data set, we're going to be using the makeBlobs function that we imported at the beginning of the notebook. And we're going to create 300 data points with 2 classes, a random seed of 42, and we'll add a standard deviation of 3, which will add some noise to our data. And before using the data, let's normalize it a bit by dividing x by the maximum x value. And then we can look at the shapes. So there's 300 training examples and 2 features. Now let's initialize some weight and bias values and see what the decision boundary looks like before training the model. Alright, so here we have an initialized weight vector with 2 elements and a bias of a single scalar element. So let's plot the decision boundary of this to see how our model looks before training. Alright, and it obviously looks like our model has not trained yet because our decision boundary is way down to the bottom and everything is being predicted as a y hat equal to 1. So now let's train our model and see if we can get some improved results. Okay, so our cost started at around 0.86 and went down to about 0.6. Let's plot that history. So it looks like our cost went down over the iterations pretty smoothly, and it almost looks like we could train more, but let's go ahead and plot our results. Alright, this is a little bit hard to see, so let's actually update our plot function. So what we saw is we need to limit the vertical axis or the y-axis, and to do that we can write this. So that'll set the lower and upper boundary for the plot according to the lower and upper points in our training data. And we can also add some spacing to that, so maybe 0.1. And let's test that new function. Okay, so that looks a little bit better, and it looks like our decision boundary is cutting almost perfectly through our data, where y equals 0 and y hat equals 0 is generally on the left, while y1 and y hat 1 is generally on the right. And it looks like we could actually train this a little bit longer, especially considering this history graph. But that can be a little exercise if you want to continue to experiment with this model. Alright, and that's about it for multiple logistic regression. Thanks for watching, and if you have any questions, make sure to leave a comment. And if you want to see more videos like this, make sure to subscribe and like the video.